Okay. So, hello everyone, my name is Gwendal Jouneaux, and I will present you my last paper, Adaptive Structural Operational Semantics, to joint work between the diverse team in Rennes, people from University of Amsterdam and McGill. So before talking about languages, first I want to introduce a bit about the software that we build with. So nowadays, software evolve in complex and changing environments, such as IoT or embedded systems, and we see more and more the need for dynamic adaptation to best deliver the services. So for example, Netflix adapt the quality of the video they send you, depending on, among other, your bandwidth. And so what we argue is that as a consequence, there is a need to provide abstractions for self-adaptation, not for when it's primary concern, like Netflix, where you want to tailor everything by hand, but when it's a secondary, but nevertheless an important concern. So the abstraction for self-adaptation is a problem studied in other communities, basically in the self-adaptive system community. And solutions have been proposed. So for example, there are multiple architectural solutions, such as the McGill loop, the Frölich architecture, or the Morph architecture. And they also provide frameworks, such as DCL, executable runtime mega models, and Ponder2, which even have a DSL to define your self-adaptive system. But the problem is that if you want or have already a DSL to capitalize your domain knowledge, it can be difficult to integrate those architectural solution frameworks. So, as we know, DSLs are tools for experts with the appropriate construct for the given domain. But if your domain does not have as a primary concern self-adaptation, you have to basically implement in the programs or in the systems your own self-adaptation, which, if you want to use frameworks or architectural solution, it require re-implementation, for example, for frameworks, which can be tedious or even impossible in some case when you don't have the primitives in the DSLs. And that also require expertise in self-adaptation from the language user, which is not always the case if it's not primary concern of the DSL. So, as an example, I will talk about the small language named RobLANG, which is a procedural DSL to program robot missions, which provide abstraction for robot sensor and actuator. And for instance, in this kind of DSL, what we might want to do is to adapt, for example, the robot speed to save energy. It's a classical trade-off that we may want to perform. And so, if we have difficulties to use a framework or have to code that by hand, we fall back to kind of method programming where we have implementation of a kind of trade-off reasoning at the top, and after that you have the effects of this trade-off reasoning with different conditions, which can be error-prone and tedious. And for each system, you have to manually design adaptation that requires expertise to design, manual implementation of the trade-off reasoning, like I said, and to be correctly integrated within the code base, which is often not really easy. So the question is the end. Of course, if I'm giving a talk, the answer is no. So we did previous work on that with the SEALS framework, published at SLE 2 years ago. The idea of the SEALS framework is a framework to implement DSLs with self-adaptive operational semantics. What we mean by self-adaptive operational semantics is that your operational semantics will change at runtime based on the result of a feedback loop that will drive some adaptations of the semantic rules, basically. And in addition, this framework also provides modularity for designing this adaptation, so you can just decorrelate the creation of the self-adaptive DSL and the creation of the adaptation in themselves. So the way the SEALS framework works, Basically, you free the DSL user from implementing the feedback loop and associated trade-off reasoning and integrate execution variants, which are the adaptation. And for the DSL designer, you have modeling capacities for modeling domain concept and also to specialize the feedback loop and the adaptation process in general. But the problem is that it's mainly an implementation framework, so we cannot specify our DSL with that. And particularly, it became hard to reason about because basically Java implementation. So what we want and what I want to present today is ASOS, so Adaptive Structural Operational Semantics, which is a meta-language to specify and reason about such self-adaptable operational semantics. So ASOS is defined as an extension of MSOS, so Modular Structural Operational Semantics. So we based on MSOS because it's a meta-language to define operational semantics, which is the domain that we want to target, as a modular definition of semantics rule, which fits what we want to do with modular adaptation, and provide the ability to verify some properties such as determinism, completeness, or determinism in some case. So we extended MSOS with by providing additional adaptation rules and how to introduce them in the semantics of the language. And from this definition, we generate an implementation with seals that use the seal framework. So our approach is around the definition of the DSL, so the language definition using ASOS. You have to define mainly three things. So the abstract syntax with metamodel, your semantics rule with the ASOS meta-language, and you have also to configure the feedback loop by giving some properties of interest for the trade-off and resources. And basically, the operational semantics that you encode with ASOS is defined as a default semantic, which is the usual semantics for your DSL. Adaptation semantics, which is additional rules to adapt this default behavior, and point cuts to express when and where to weave this adaptation semantics. So let's talk a bit about the code right now. So this is an ASOS definition of some rules of semantics. So the first instruction is basically the model or where to import the abstract syntax. So the idea is that our syntax is presented as a meta model that we merge with another meta model that represents the dynamic information that we merge to have an execution meta model on which we can operate. And in addition to that, this semantic definition is composed of a set of semantic rules. So you have, for example, here the rule program, that is the root rule for our DSL, which define a conclusion as a transition between terms. So here you have the term program with a subterm command, and this rule results in another program with a new command that has been partially evaluated, and that has meant progress. In addition to those, conclusions, you can provide some premises that help you either compute subterms or define a condition to call those rules. So, for example, the resolve keyword here is defining the section of the premise, and here we have a premise that said that if the command can progress to a new command, then the program has advanced also. So the idea is that if we can execute the command to a new state, then the whole program has advanced to a new state. We have two kinds of transition premise. So the first one, which is the classic one, was we also have termination premise. So the termination keyword is to deal with abrupt termination in the semantics. So for example, if you want to implement a break, a return, or exceptions, you might want you want to stop the execution of the current control flow and just fall back to some rules. And so to do so, you have the termination keyword, which, given as an output of the conclusion rule, will just throw emit a signal of termination with some dynamic values. So here, for example, we talk about runtime errors. And in your premises, you can just catch that to manage and continue and fall back to another behavior. So for example, if you get a return, you can just get the value and say that the function returned this value. So in addition to transition premise, we provide bindings. That's, the bind section is related to computing values and storing values, basically. So in this case, you have self.value. So this value is coming from the dynamic information that were weaved with the meta model. And the self refers to the assignment that is in the input of the rule. So basically, what we say here is that the current value of the variable which is assigned is the integer that has been computed from the expression, basically. And finally, we have the where clause, where you can express first-order logic conditions, allowing, for example, to know if you have to go into the then branch or the else branch of a if concept, for example. And so, in addition to those semantic rules, and so the semantic rules provided the semantics for the default semantics, but we can also express adaptations on top of those rules. So here is, for example, the definition of an adaptation module, which is approximate double, where we have mainly two kinds of things inside those modules. First, matching definition, which is the point cuts of our adaptation, where we have a structural matching over nodes, saying that we want to apply some rules at some point if we are in a subtree from an assignment, which has a varref, for example. And we can also express additional constraints through the where clause. So, for example, here we target an assignment where the value that is assigned to a variable of type float. And after this matching definition, we also can express adaptation rules. So adaptation rules are extended semantic rules. So the first thing that you specify here is the kind of adaptation. You have three kinds of adaptation: before, after, and specialized, that will weave the new rules inside the semantics before, after the specified rules or in place of the specified rules. So, for example, here the before binup right hand side specified that the rule binup left hand side to float that is defined after should be called before calling the binup right-hand side rule, basically. So if we take a look, step back and look at the meta model, what I showed you is that we have a definition of adaptive operational semantics, which is for the default semantics composed of rules. Those rules contain at least one transition that represent the conclusion and the effect of the rules, and potentially some premises that express the continuation of the computation to child of the node in the AST, for example. We have also the different clauses, so the bindings, the condition, but also I did not show, but we also have input and output that allow you to communicate with the outside of the language. So, for example, input is for user input in the console, and output for example, printing in the terminal, for example. And the second part of the adaptive operational semantics is the adaptation modules. that are composed of a match, one or more match clauses that define when to introduce the adaptation rules, and adaptation rules that can be before specialized or after rules, kind of adaptation that target one rules and define another rule. So now that we know a bit more about the syntax of the metalanguage, we provided some formal semantics. I will not go too much into the detail of that, but the core idea is that we have to decide if we apply an adaptation or apply the default semantics. And so the translation of this rule is basically saying that if you first you get the set of possible adaptation or activated adaptation that you might want to apply. And if you select the correct one given the matching that you have, if you have at some point one rule that one adaptation rule that that can be executed, you call it, and if you cannot here, then you fall back to the default semantics, which is basically how we proceed. But if you want to have more detail, you can take a look at the paper where it's more clearly explained. So on top of that, we provide a translational semantics from ASOS to SEALs to be able to execute the semantics. So the idea is the same structure of rule from ASOS. We first generate words which correspond to verifying that the current term is corresponding to the pattern, the input pattern in the conclusion of the rule, so that's the little one. After that, we check some conditions, so the conditions that were expressed in the where clause, and we resolve premise to check if the output of the premise is corresponding to the term. So, for example, you've seen before the output termination runtime error, so we'll check if it's correctly runtime error or not. If it's not, we don't call this rule, but another. And if all those checks are passed, we then enter the effects part, so it's really applying the rule. So we just call, we basically translate the input and get the information from the outside, compute the different bindings that we can have. Then we actually compute the term, the output term, which can be done in different way. So for example, you can just update the current node, or you can return a value. Same here, if you want more detail on how we exactly proceed, you can take a look at the paper. And finally, we manage some of the outputs. So for example, print statement. And inside this generated effect, you have the input point for the different code for the adaptations. So now we generate this code, but how that is executed. So the first part when you call a rule on a node is to perform the feedback loop to know if there is some adaptation. So you will first monitor, analyze, plan, and execute by selecting the different modules that can be applied with respect to the trade-off and the current context. And based on that, you will have the second part of the process, which is basically matching those activated adaptation modules to the current node to see if the node matches those adaptation, to sort out the applicable adaptation rules. And then after we enter the process of just checking if the rule exists and call the adaptation rules one after another and select in the case of specialize because we replace and not add just a new rule. So to evaluate this work, we provide some proof on top of the formal model that we provided in the paper. So basically, we check determinism and completeness of the semantics that we define using ASOS. And about non-termination, what we can do currently is that we can detect patterns that we know will provide, will cause, for example, race condition and cycle between adaptations. But we currently overestimate because, for example, the feedback loop, the concrete the feedback loop step are not yet modeled in the formal model. So, for example, we cannot detect if two adaptation rules would create a race condition, but they will never because their matching the feedback loop made them never appear together, for example. In addition, on the more executable part, we check the applicability on the RobLANG DSL by providing adaptation to a program to slow the motor speeds to save energy. And we observe correct adaptation behavior, and we also observe that when changing the trade-off and dynamically, we are able to adapt to the change in this context. So that is okay. And on the second experiment, we wanted to check the performance of that. So compared to manually implementing the adaptation process inside the RobLANG program. So we made an experimental setup with a machine where we executed 30 times the experiment with 3 times with reboot to mitigate the effect of initial state to try to have a proper setup. And the results are a bit, well, at first were strange because we gain actually speed. But our theory right now is that's probably from JVM optimization because the feedback loop in our case, so using ASOS, is defined using Java, while in RobLANG it's in RobLANG. And so probably some JVM optimization help us in the performance here. So as a conclusion, the ASOS metalanguage provides abstraction for defining operational semantics and their adaptations. We also provide mechanism for composing adaptation with the default semantics at runtime, so basically calling them. And we also provide support for verifying properties on those semantics. On the technical aspect, we provide the IDE tool support for ASOS in an Eclipse environment, generator targeting the sales framework, and we are also fully compatible with Xtext, which means that you can define your DSL in Xtext and just provide semantics as an ASOS semantics, and it should work. And the perspective of this work is that, well, first, evaluate the complexity of using ASOS because it's declarative and rule-based language. It's not the same as expressing that as, let's say, a visitor pattern for implementing the semantics. So we have to assess the complexity of that. We also want to verify the correctness envelope, so the way that we constrain what are the possible adaptations that were present in SILD that we do not make in ASOS because we don't really know how to constrain rules right now in the way that we want. And we also want to extend ASOS to configure the feedback loops, which is basically what I said earlier when I was talking about disambiguating some detection in the non-termination. And we also want to use ASOS declarative nature to support SAL composition and make language composition, self-adaptable language composition. Thanks for your attention, and if you have any question.
Thank you, Gwendal. Do we have any questions?
Thank you very much for the talk, and also thank you for your interest in modular SOS, which isn't a very popular framework. At the beginning of section 4 in the paper, you say you motivate these adaptation rules and the extension to the MSOS framework by saying that It allows to express structural patterns that are not possible to express using the typical MSOS rule format. Have you proved that?
No.
Give a reference.
Okay, that's maybe not the right way to put it. The idea was, when we were writing this, is that if you want to have some property like dissimulation as a concurrence, your pattern just, you cannot nest so much pattern, while our matching pattern can be arbitrarily deep. So that was the idea around that. By allowing this matching deeper, it cannot be represented using MSOS without breaking this property, and that's what we said.
Another question? Yes.
Yes, maybe one brief question first. Thank you for the talk, very interesting. I have one question regarding the checking of the validity of what you can translate and what not. I mean, we just heard about the structural features, but just from a behavior point of view, as Java is Turing complete, I would hope that, well, you can translate nearly everything which is feasible. Can you give an example of what absolutely makes no sense to translate, and how would you deal with that?
You mean translate from Java to ASOS?
No, I think the other way around.
The other way?
So you have your ASOS rules and translate to Java, or did I get that wrong?
Yeah, that's basically what we do in the generator, in fact. And no, I don't see really any problem of generation.
Okay, but why is then this checking step, if you can, whether you can translate something?
By checking step, you mean the generated word?
It was a slide or two before, I think. There's no valid adaptation transitions. Maybe I got that wrong.
No valid transition is that, for example, you have some adaptations that are active and that are, for example, for the assignment, but you have an assignment. If we take, for example, the previous example, which is, well, so long ago. So, for example, here we target assignment that are tab float. So you have a module that is activated, but is not matching, so we do not provide these rules. So we have to check if those rules are available when we are executing, basically. So that's what's in.
Thank you.
Okay, thank you, Gwendal.